Hello and welcome to Boring Sleepy Scientist. I'm glad you're here. Whether you've had a long day, a mind that won't quiet down, or you simply find peace in the gentle hum of the cosmos. Are you winding down under city lights, or nestled somewhere quiet and dark, perhaps with a cup of something warm? If you enjoy these sleepy explorations, I'd be so grateful if you gave the video a little like and tapped that subscribe button. Helps more boring sleepy scientists like you find their way here, and it means I can keep making more of these soft, starlit journeys for you. This video is made just for you. Tonight, we'll be embarking on perhaps our oldest journey yet, reaching back to the very dawn of time to uncover the universe's most ancient whisper, the cosmic microwave background. It's the faint uniform glow that permeates everything, the oldest light, a quiet echo of the Big Bang itself. But before we begin this soft exploration, I'd love to know where in the world you are listening from and what time it is where you are right now. Now, I do hope this video isn't too interesting, though if it does accidentally keep you awake, at least you'll come away knowing a bit more about how our universe truly began. Not such a bad trade, really. So settle in, close your eyes if you like, and let's take a slow, thoughtful wander through the story of the universe's first light. To truly appreciate the cosmic microwave background, we must first try to imagine a time, an epoch, when the universe was fundamentally different from the vast, dark, star-filled expanse we see today. Close your eyes and let your mind drift back. Not just millions, but billions of years. Imagine the very earliest moments after what we call the Big Bang. This wasn't an explosion in space, but an expansion of space itself. And in those initial fractions of a second, the universe was unfathomably hot and dense. So hot, in fact, that matter as we know it couldn't exist in stable forms. Think of it as a primordial soup, but not a liquid soup. It was a plasma. Now, a plasma is often called the fourth state of matter, beyond solid, liquid, and gas. It's like a gas, but one where the atoms are so incredibly hot that their electrons have been stripped away from their nuclei. So, instead of neutral atoms, you have a chaotic, energetic mix of free-floating protons, neutrons, and electrons, along with countless photons, the tiny packets of light energy we've discussed before. In this superheated, super-dense environment, light simply could not travel freely. Imagine trying to walk through an incredibly crowded room where everyone is constantly bumping into everyone else.
Ow.
Where the air itself is thick with swirling particles. That's what it was like for a photon in the early universe. Every time a photon tried to move a tiny distance, even a fraction of a millimeter, it would immediately collide with a free electron. It would be absorbed, then re-emitted, only to almost immediately hit another electron. And so on, in an endless, rapid-fire sequence of scattering. This constant scattering meant the universe was opaque. Think of a very, very thick fog, so dense that you can't see your hand in front of your face, or the inside of a star where light is constantly generated but takes thousands of years to slowly, laboriously make its way to the surface, bouncing off countless particles along the way. That's what the entire universe was like for its first few 100,000 years. There was light, yes, an immense amount of it, but it was trapped, unable to escape the dense ionized plasma. It was an undifferentiated, brilliant, featureless glow, but a glow you couldn't see through. It permeated everything, yet revealed nothing beyond itself. There were no distinct forms, no shadows, no stars, no galaxies. Just this brilliant, uniform, chaotic soup of energy and matter, unable to fully illuminate itself. This period, from roughly a few minutes after the Big Bang until about 380,000 years later, is often described as the photon epoch, or the dark ages of the universe. The term dark ages can be a little misleading, as it wasn't dark in the sense of lacking light, but dark in the sense that light couldn't travel far enough to form images or reveal structure. It was a time when the universe was incandescent, but blind. A time of trapped light, the universe waiting to see itself. As time passed, the universe continued its relentless expansion. This expansion wasn't like a balloon inflating into existing space. It was space itself stretching, growing, spreading out. And as space expanded, it had a crucial effect. It caused the universe to cool down. Imagine a gas expanding in a container. As it expands, its temperature drops. The same principle applies to the entire cosmos. Slowly, gently, over hundreds of thousands of years, the average temperature of the universe fell from trillions of degrees to billions, then millions, and finally, down to a critical threshold. This threshold was around 3,000 Kelvin, or about 2,700 degrees Celsius, which is still incredibly hot by earthly standards, hot enough to melt most metals, but a dramatic decrease from the initial inferno. Until this moment, the universe was too hot for electrons to reliably settle into orbits around atomic nuclei. The free electrons were moving too energetically. Anytime an electron tried to bind with a proton to form a neutral atom of hydrogen, a high-energy photon would come along, collide with it, and immediately knock the electron free again. It was a constant battle, and the photons were winning, keeping everything ionized and separated. But once the temperature dropped below that critical 3,000 Kelvin, the photons simply weren't energetic enough, on average, to constantly ionize the hydrogen and helium. The electrons finally could overcome the scattering forces and combine with the protons and helium nuclei. They recombined to form the very first stable neutral atoms in the universe, mostly hydrogen and helium. And here's why decoupling is the more evocative term for light. Once those electrons were bound within neutral atoms, they were no longer free to constantly scatter photons. It was as if the cosmic fog had suddenly lifted, the smoke cleared, the crowded room emptied out. The universe, which had been opaque for 380,000 years, suddenly became transparent. The photons, these tireless, restless particles of light, which had been trapped in an endless pinball game of scattering, were now free. They had no more obstacles. They began to stream out in every direction, no longer interacting with matter. They just went. They set off on their long, uninterrupted journey across the vast, expanding cosmic landscape. This moment, this cosmic clearing, is the birth of the cosmic microwave background. It is the moment the universe truly began to shine through itself. It's the initial flash, the glorious release of light that had been held captive. Now free to traverse the nascent cosmos, carrying with it the imprints of that ancient time. This light, the oldest light we can ever hope to see, is the direct visual evidence of the universe's transition from an opaque plasma to a transparent, atom-filled space. Finally able to travel to our detectors billions of years later, it is quite literally the first light from the beginning of everything. So, these photons, released in that momentous instant of decoupling, began their long, long journey. They set off in every conceivable direction, traversing the rapidly expanding cosmos for nearly 14 billion years. But if they were released when the universe was hot and glowing at 3000 Kelvin, why do we detect them today as faint microwaves, just a few degrees above absolute zero? This is one of the most elegant and profound effects of the universe's continuous expansion, the phenomenon of cosmic redshift. Imagine, if you will, a long, stretchy rubber band. Now, draw a wave on that rubber band. As you stretch the rubber band, what happens to the wave? It gets longer, doesn't it? Its peaks and troughs spread further apart. This is precisely what happens to light waves as they travel through the expanding universe. The very fabric of space itself is stretching, and as it stretches, it elongates the wavelengths of the photons traveling through it. When these photons were first released, their wavelengths were relatively short, corresponding to high-energy light. They were primarily in the visible and near-infrared parts of the electromagnetic spectrum, akin to the orange-red glow of a hot object. But as they traveled for billions of years, the universe grew vastly larger. The cosmic rubber band stretched and stretched and stretched. This stretching of space caused the wavelengths of these photons to continuously increase. An increase in wavelength corresponds to a decrease in energy and a shift towards the redder, longer wavelength end of the electromagnetic spectrum. It's like taking a vibrant, energetic red light and gently stretching it until it becomes a lazy, languid radio wave. This is why we call it redshift, because visible light shifts towards the red end of the spectrum. But these ancient photons have been stretched so much that they've moved far, far past the visible red. They've journeyed through infrared, then through the far-infrared, and finally settled squarely into the microwave portion of the spectrum. Their energy has been diluted by this cosmic stretching. Their original temperature of about 3000 Kelvin has been cooled by the expansion of space itself, effectively reducing their observed temperature today to a mere 2.725 Kelvin. It's just about 2.7 degrees Celsius above absolute zero. The theoretical temperature where all atomic motion stops. So when we detect the cosmic microwave background today, we're literally catching photons that have been traveling for 13.8 billion years. Photons that originated from the universe when it was just 380,000 years old. These photons bear the imprints of that ancient, hot, dense state. But their wavelengths have been stretched and cooled by the immense journey through an expanding cosmos. They are no longer a blazing inferno. They are a faint, pervasive, uniform microwave glow. A gentle hum that reaches us from every direction, carrying the most ancient message of all. It's a testament to the universe's incredible ability to preserve and transform information over cosmic timescales. For countless millennia, this gentle hum of the universe, this faint afterglow of creation, permeated everything, passed through us, through our planet, through our very bodies. Yet, it remained utterly undetectable to human senses, and for most of our scientific history, entirely unknown. The tools and the understanding simply weren't there. However, the theoretical groundwork for its existence was being laid quietly in the background. In the 1940s, physicists like George Gamow, Ralph Alpher, and Robert Herman were working on the Big Bang Theory, trying to understand the origin of the chemical elements. Their calculations predicted that if the universe had indeed started from a hot, dense state, there should be a leftover, uniform background radiation, a sort of fossilized heat. They even estimated its temperature to be a few degrees above absolute zero. Their predictions, though groundbreaking, were largely overlooked are not taken seriously enough to spur immediate experimental verification at the time. The scientific community was still debating the Big Bang versus the steady-state theory, and Gamo's ideas were seen as somewhat speculative. Fast forward to the early 1960s. At Princeton University, a group of physicists led by Robert Dicke was independently coming to similar conclusions. They were explicitly looking for this residual radiation, calculating that if it existed, it should be detectable in the microwave range. They even began building a special antenna for this purpose, eager to be the ones to make this monumental discovery. But fate, as it often does in science, had a wonderfully ironic twist in store. About 48 kilometers away, at Bell Telephone Laboratories in Holmdel, New Jersey, two American radio astronomers, Arno Penzias and Robert Wilson, were struggling with a very different problem. They were using a brand new cutting-edge 6-meter horn-shaped antenna state-of-the-art instrument designed for very sensitive satellite communication experiments, particularly for the Echo and Telstar satellite projects. Their goal was to calibrate their antenna to detect extremely faint radio signals. However, no matter what they did, they kept encountering a persistent, annoying, low-level noise, or static in their receiver. This noise was baffling. It came from every direction in the sky, uniformly. It didn't vary with the time of day, the season, or the position of the Earth relative to the Sun or Milky Way. It wasn't terrestrial interference, nor was it related to their equipment. Penzias and Wilson, being meticulous scientists, tried everything they could think of to eliminate this mysterious background hum. They suspected equipment malfunction, so they cooled their receiver to super low temperatures. They painstakingly checked every connection. And then, in a rather famous anecdote, they considered the presence of a pair of pigeons who had decided to nest inside the horn antenna. They cleaned out the antenna, removing what Penzias famously referred to as white dielectric material pigeon droppings. They even briefly relocated the pigeons, yet the persistent uniform background noise remained. It was a faint, continuous, low-level hiss that just would not go away. Frustrated, and having exhausted all conventional explanations, Penzias, almost on a whim, decided to call Bernard Burke, a colleague who knew about Dicke's work at Princeton. Burke, connecting the dots, realized what Penzias and Wilson had stumbled upon. He immediately suggested they contact Dicke. When Penzias and Wilson described their unexplained excess noise to Dicke and his team, there was a moment of profound realization. Dicke reportedly turned to his colleagues and said, "Boys, we've been scooped." Penzias and Wilson, entirely by accident, had already found the very thing the Princeton group had been actively searching for. In 1965, Penzias and Wilson published their findings in a paper titled "A Measurement of Excess Antenna. Temperature at 4080 MCS." In the same edition of the Astrophysical Journal, Dicke and his colleagues published a companion paper, "Cosmic Blackbody Radiation, Providing the Cosmological Interpretation of the Noise." This simultaneous publication marked a turning point in cosmology. The persistent static, the pigeon droppings, the baffling background hum was all in fact the cosmic microwave background, the unmistakable echo of the Big Bang. Penzias and Wilson were awarded the Nobel Prize in Physics in 1978 for their discovery. It was a classic example of serendipity in science, being prepared to observe something unusual, then having the intellectual curiosity and open-mindedness to consider its profound implications. This accidental discovery provided the single strongest piece of observational evidence supporting the Big Bang theory. transforming it from a compelling idea into the standard model of cosmology. It was the universe's clearest, most direct message from the dawn of time, heard, finally, by two baffled but brilliant astronomers. The initial detection of the cosmic microwave background by Penzias and Wilson was a monumental breakthrough, confirming the Big Bang's fundamental prediction. But their simple, uniform detection was just the beginning. The real secrets, the universe's most ancient whispers, lay hidden within tiny, subtle variations in this pervasive glow. Like a very, very quiet lullaby, there were nuances in its sound, variations in its uniform texture. Imagine a perfectly smooth, perfectly round marble. Now imagine a marble that, to the naked eye, still looks perfectly smooth and round, but under a powerful microscope. You can see incredibly tiny bumps and dimples, microscopic imperfections. The early measurements of the CMB made the universe look like the perfectly smooth marble. It was remarkably uniform, the same temperature in every direction down to a tiny fraction of a degree. This uniformity was important. It told us the early universe was very homogeneous, very consistent. However, theory predicted that there had to be tiny imperfections, tiny fluctuations in that early soup of matter and energy. Without these lumps and bumps, gravity would have had nothing to pull on. The universe would have remained a smooth, featureless expanse, and stars and galaxies would never have formed. The very existence of everything we see today, including us, depended on these initial, minuscule irregularities. The challenge was to find them. This required a new generation of incredibly sensitive instruments, capable of detecting temperature differences as small as a few parts in 100,000. It was like trying to measure the temperature of the entire Earth and detecting a difference of a tiny fraction of a degree from one side to the other. Enter the satellite missions. COBE satellite. This was the trailblazer. After years of meticulous calibration and data analysis, the COBE team, led by John C. Mather and George F. Smoot, finally detected these tiny temperature fluctuations in the CMB in 1992. It was a monumental discovery. The universe wasn't perfectly smooth after all. It had tiny primordial wrinkles. COBE's data confirmed that the CMB had a perfect black body spectrum. Exactly what you'd expect from the cool-down radiation of a hot, dense, early universe. This was like hearing the clearest, most perfectly tuned note from the universe's beginning. WMAP satellite. WMAP was COBE's successor. It's designed to map these fluctuations with far greater precision and resolution. Over 9 years, WMAP created incredibly detailed maps of the CMB anisotropies. These maps, often depicted as beautiful modeled oval images, are essentially the baby picture of our universe, when it was just 380,000 years old. They show the tiny hot and cold spots that were the seeds of all cosmic structure. WMAP's data allowed scientists to determine key cosmological parameters with unprecedented accuracy, including the age of the universe, refining it to 13.77 billion years old, the composition of the universe, revealing that normal matter makes up only about 4.9% of the universe. Dark matter makes up about 26.8%. And dark energy accounts for about 68.3%. These percentages were revolutionary. The geometry of the universe, showing that the universe is remarkably flat on large scales, meaning it will likely continue expanding forever, rather than eventually collapsing back in on itself. Planck satellite. The European Space Agency's Planck mission was the ultimate CMB mapping machine. It's providing the most detailed and precise picture of the CMB anisotropies to date. Planck's data pushed the precision even further, confirming and refining WMAP's findings and adding even more subtle details to our understanding. It allowed us to hear the universe's lullaby with incredible clarity, revealing slight deviations that hint at even deeper physics. So what do these tiny, tiny fluctuations in temperature actually tell us? The seeds of structure. They are the gravitational seeds from which everything we see today grew. The slightly hotter regions were where matter began to clump together under gravity, slowly, patiently forming the first galaxies. Clusters and superclusters. The slightly cooler regions became the voids between these structures. Without these initial variations, the universe would still be a uniform, featureless gas. Confirmation of inflation. The patterns and statistical properties of these fluctuations provide strong evidence for the theory of cosmic inflation. A hypothesized period of incredibly rapid, exponential expansion that occurred in the first tiny fraction of a second after the Big Bang. Inflation would have smoothed out any initial irregularities and stretched quantum fluctuations to cosmic scales, leaving precisely the kind of temperature variations observed in the CMB. Understanding cosmic composition. By precisely measuring the peaks and troughs in the CMB's power spectrum, cosmologists can infer the relative amounts of baryonic matter, dark matter, and dark energy in the universe. It's like analyzing the unique fingerprint of the universe's early ingredients. The universe's flatness, the size and spacing of the largest hot and cold spots in the CMB maps, directly indicate the overall curvature of space. The data overwhelmingly points to a geometrically flat universe, meaning that parallel lines remain parallel on cosmic scales. And the angles of a large triangle add up to exactly 180 degrees. This flatness is a crucial piece of the puzzle for understanding the universe's ultimate fate. In essence, the cosmic microwave background isn't just an echo. It's a cosmic blueprint. It's the most ancient, most accurate, and most encompassing weather map of the early universe, revealing the primordial conditions from which all existence unfolded. It allows us to peer back in time with unprecedented clarity, listening to the universe's first whispers and understanding how it grew from a hot, dense plasma into the grand, structured cosmos we inhabit today. It is truly the universe's baby picture, taken at a time when it was just a tiny fraction of its current age. Perhaps the most profound and comforting thought about the cosmic microwave background is its constant quiet pervasion. It's not some distant abstract phenomenon confined to academic papers or specialized observatories. It is here. It is now. It is everywhere. As you lie there, perhaps drifting deeper into relaxation, consider this. Billions upon billions of these ancient, red-shifted photons are passing through you at this very moment. They are streaming through the walls of your room, through your bed, through your body, through the entire planet, completely unimpeded. They originated from a time before stars existed, before galaxies formed. From that very moment, nearly 14 billion years ago, when the universe became transparent. They are the oldest light, and they are gently bathing everything in their presence always. Think of it. Every atom in your body, every structure around you, every living thing on Earth is constantly permeated by this cosmic background radiation. We are literally swimming in the afterglow of the Big Bang. It's a silent, invisible embrace from the very beginning of time. This pervasive hum, though imperceptible to our senses, without sophisticated instruments, is a constant reminder of our deep connection to the origins of everything. It speaks to a fundamental principle of the universe: continuity. That first light, that initial release, continues its journey, constantly expanding, cooling and stretching, but never truly vanishing. It's like an eternal echo, reverberating softly through the cosmic corridors, reaching every corner, every speck of dust, every living being. This constant presence also has subtle, real-world implications, even if they aren't immediately obvious to us. For astronomers, detecting this background noise is critical. It sets a fundamental limit on how dark the sky can ever be for microwave observations. It's a baseline, a constant cosmic hum that all other microwave signals must contend with. For spacecraft, especially those designed for deep space missions, the CMB provides a steady, uniform radiation background that needs to be factored into their design and operation. It's a tiny, universal warmth they continuously experience. But beyond the scientific and technical aspects, there's a deeply poetic and philosophical dimension to the CMB's omnipresence. It means that the universe, in a very tangible way, carries its past with it, everywhere, always. The Big Bang wasn't a singular event that happened far away and then left no trace. It left this luminous, pervasive footprint, ensuring that we are perpetually reminded of our cosmic origins. It means there's no true empty space. In the universe, even the emptiest void between galaxies is filled with this faint, ancient light. It turns the seemingly vast and indifferent cosmos into something deeply intimate, something that whispers its beginning into our very existence. It's a source of profound comfort, a sense of belonging to something immeasurably grand and ancient. And in a sleepy, quiet way, it's a source of calm. There is a cosmic stability in this omnipresent hum. No matter how chaotic our immediate world may seem, no matter how fast our lives may feel, the universe itself, at its most fundamental level, continues to hum its ancient, steady song, a uniform, unwavering, silent rhythm. It's a background melody that has been playing for billions of years, a constant reminder of the universe's immense scale and its patient unfolding story. So, as you settle deeper into your rest and your thoughts drift with the stars, remember that even in the quietest moments, even in the deepest dark, the universe is softly, gently, and constantly humming its first lullaby. A lullaby made of the oldest light. Always there, always present, a testament to the enduring mystery and beauty of creation. Even after decades of study and incredibly precise measurements, the cosmic microwave background continues to be a source of active research and profound insight. Yes. It's a testament to its richness that we are still learning from this ancient light, probing its subtlest details to uncover even more about the universe's beginning and its ultimate fate. Think of light as a wave that vibrates. Most light vibrates in all directions. But sometimes, light can become polarized, meaning its vibrations are aligned in a specific direction. When light from the CMB was last scattered by free electrons during decoupling, it left a subtle imprint of its polarization. Detecting and mapping this polarization can provide even deeper insights into the conditions of the early universe. The baby picture of the universe continues to reveal new features as our scientific magnifying glass gets ever more powerful. One of the most exciting frontiers in CMB research involves looking for incredibly faint patterns in its polarization. There are two main types of polarization patterns that cosmologists are looking for in the CMB. E-modes. These are patterns that indicate density fluctuations and gravitational lensing. They have been successfully detected and provide a wealth of information that reinforces what we've learned from the temperature fluctuations. They're like seeing the subtle brushstrokes that created the initial cosmic landscape. B-modes. These are much more elusive and incredibly exciting. They are patterns that theoretical physicists predict would have been generated by primordial gravitational waves. If cosmic inflation truly happened in the very first fractions of a second after the Big Bang, it would have created ripples in space-time itself. Gravitational waves. These waves would have left a unique, swirling polarization pattern on the CMB. Detecting these B-modes would be direct evidence of inflation. A monumental discovery that would revolutionize our understanding of the universe's absolute earliest moments. It would be like hearing the very first tiny ripple of creation, the subtle echo of the universe's dramatic birth pangs. While some tentative detections of B-modes have been announced, the search is ongoing with dedicated ground-based telescopes and future satellite missions. It's an incredibly challenging measurement, requiring extreme sensitivity and careful removal of foreground contamination from our own galaxy. But the potential payoff is immense, a direct window into a realm of physics far beyond anything we can replicate in a lab. Beyond polarization, future CMB experiments aim to map with even higher resolution, like upgrading from a grainy photo to a crystal clear image, allowing us to see even finer details in the primordial ripples. Probe smaller scales, looking for subtle deviations that might hint at new particles or interactions in the very early universe. Study the missing energy. The CMB helps us understand the ratios of ordinary matter, dark matter, and dark energy. Future observations might provide even deeper clues about the mysterious nature of dark matter and dark energy, which together make up about 95% of our universe but remain largely unknown. Look for signs of cosmic strings or other exotic phenomena. While less likely, some theories predict very specific, faint imprints on the CMB that could reveal exotic forms of matter or energy from the early universe. The CMB is also crucial for understanding the cosmic dark ages that followed decoupling before the first stars lit up. The CMB photons traveled freely through this period, and their interactions, or lack thereof, with the neutral hydrogen gas can provide clues about when and how the first stars and quasars began to reionize the universe, changing its transparent state back into a slightly ionized one. In essence, the cosmic microwave background is a bridge between the incredibly hot, dense, quantum-dominated universe of the Big Bang and the vast, structured cosmos we inhabit today. It is the clearest, most direct, and most reliable witness to the universe's formative years. Every new, more precise measurement of its subtle features brings us closer to understanding not just what happened in the early universe, but why it happened that way, and what fundamental laws governed its first moments. It's a testament to human curiosity and ingenuity that we can not only detect this faint, ancient glow, but also decode its intricate patterns to reveal so much about the universe's past. The CMB continues to be a quiet, constant guide, whispering secrets across billions of years, inviting us to listen ever more closely to the story of everything. As our quiet journey through the cosmic microwave background comes to its gentle close, Let's take a moment for reflection. We've explored the universe's earliest moments, glimpsed its opacity, witnessed its grand clearing, and traced the billions of years-long journey of its first light. We've marveled at a serendipitous discovery and pondered the profound secrets locked within tiny temperature fluctuations. But what does this ancient, pervasive hum truly mean for us, here and now, drifting towards sleep on a small planet in a vast cosmos? The cosmic microwave background is, in many ways, the ultimate reminder of our cosmic origins and our deep connection to the universe itself. Every atom in your body, every breath you take, every thought you think, exists within this sea of ancient light. You are literally bathed in the afterglow of creation. This isn't just a scientific fact. It's a profound, almost spiritual truth. We are not separate observers of the universe. We are an integral part of its unfolding story, constantly touched by its oldest whisper. It offers a unique perspective on time. When we look at the stars, we are seeing them as they were, years or even millennia ago. But when we look at the CMB, we are looking back across nearly the entire age of the universe. It is a direct, unfiltered glimpse into the very beginning. A moment when the universe was fundamentally different from anything we can imagine, yet contained the seeds of everything that would ever be. This ancient light acts as a kind of cosmic memory, a silent archive of the universe's earliest self. It speaks to the immense scale and elegant consistency of the universe. The fact that this radiation is so remarkably uniform across the entire sky tells us that the early universe was incredibly homogeneous. It speaks of a fundamental order, a set of underlying rules that govern the very first moments and continue to operate consistently across billions of light years. This cosmic consistency is, in its own way, very comforting. In a world that often feels chaotic and unpredictable, the universe, at its grandest scale, reveals a deep underlying harmony. The CMB is also a testament to the power of scientific inquiry, to human curiosity. We began with simple questions about the universe's origin, developed complex theories, and then, through meticulous observation and accidental discovery, found the undeniable evidence of that ancient past. It shows how patience, ingenuity, and a willingness to explore the unknown can unlock the most profound secrets of existence. It allows us to piece together a coherent narrative of our cosmic home, from its fiery birth to its current state. And finally, it is a source of peace. The cosmic microwave background is a gentle, unchanging presence. It doesn't demand attention, doesn't shout for recognition. It simply is. It flows through everything, a quiet background hum that reminds us of the universe's immense age, its enduring processes, and its quiet, continuous expansion. The whispering cosmos. Exploring silence and space here on Earth, sound is everywhere. It's the chirping of crickets outside your window, the distant rumble of traffic, the soft rustle of leaves, the gentle hum of your refrigerator. Even when we try to create silence in a soundproof room, we still hear something. The rhythmic thump of our own heart, the soft whoosh of blood in our ears, the subtle creak of the building settling. True, absolute silence is almost impossible for us to experience here on our noisy, vibrant planet. But out in space, it's different. Truly different. Space is mostly a vacuum. It's an almost perfect void. There are incredibly few particles, so few that there's nothing for sound waves to bump into, nothing to carry those vibrations. It's like a pond without water. No matter how loud an explosion, how grand a starbirth, or how dramatic a cosmic collision, if it happens in the vacuum of space, you wouldn't hear a thing. It would be utterly silent. This isn't just a quiet place. This is a place where the concept of sound simply doesn't apply. Think of an astronaut floating outside the International Space Station. Even if a wrench accidentally drifted by and gently tapped the hull, they wouldn't hear it directly. They might feel the vibration through their suit if they were touching the hull. But the sound itself, that familiar clink, would be absent. They would be enveloped in a profound universal quiet. This cosmic silence isn't entirely uniform, of course. There are exceptions. Inside a spacecraft, there's air, so you can speak and hear. Close to a dense celestial body, like a planet with an atmosphere, sound could travel. If you were somehow able to dive deep into the heart of a star, the plasma would be a very dense medium, and it would be incredibly noisy, though in ways our ears could never comprehend. But the vast stretches between stars, between galaxies, are utterly devoid of audible sound. This fundamental truth of physics that sound cannot travel through a vacuum has a subtle, powerful effect. It means that the universe, for all its grand drama of exploding stars and colliding galaxies, is performing its symphony in absolute quiet. You only hear about it when it arrives as light as radio waves. It exerts different forms of energy that don't need a medium to travel. They traverse the silent void at incredible speeds, eventually reaching our instruments or our eyes as a visual or electromagnetic echo. So when we look up at the night sky, at the twinkling stars, the fuzzy glow of distant nebulae, we are seeing events of unimaginable power and beauty unfolding in perfect, breathtaking stillness. There's no roar, no boom, just the silent ballet of gravity and light. The profound quietude. The absence of sound in space is more than just a scientific fact. It invites us to contemplate the very nature of quietude. Here on Earth, we often associate silence with emptiness or even loneliness. We fill our quiet moments with music or podcasts or the chatter of our own thoughts. We are uncomfortable with prolonged stillness. But the silence of space isn't lonely, it's majestic. It's the canvas upon which the entire cosmic story is painted. It allows the light to shine brighter, gives the stars their profound solitude. It underscores the incredible journey of photons traveling for millions, even billions of years through utter quiet to finally meet our eyes. Consider the human need for sound. We use it to communicate, to navigate, to express emotion, to create art. Our world is rich with auditory cues. Imagine if our evolutionary journey had taken a different path. If sound were not possible on our home planet, how would our societies have developed? How would we communicate? How would our art be different? The very way we experience reality is shaped by the presence of sound. So the cosmic silence highlights our terrestrial uniqueness, reminds us that our experience of reality, of noise, of music, is a very specific, earthbound phenomenon. Out there, the universe exists on different terms. It speaks in light and gravity, not in echoes and reverberations. Philosophers have often pondered the meaning of silence. For some, it's a void to be filled. For others, it's a profound space for introspection, for listening to the inner self. And in many spiritual traditions, silence is considered sacred. A gateway to deeper understanding, a way to connect with something beyond words. The silence of space takes this idea to its ultimate conclusion. It's a silence that truly is beyond words, beyond sound, beyond even the possibility of a whisper. And in that vast, natural quiet, there's a kind of permission. Permission to let go of the need for constant input. Permission to release the mental noise. Permission to simply be in the stillness. Our biological connection to sound. Our connection to sound is deeply biological. Ears are incredibly complex instruments designed to pick up the tiniest vibrations in the air. The tiny bones in our inner ear, the malleus, incus, and stapes are a marvel of engineering. Amplifying these vibrations and turning them into electrical signals for our brain to interpret. We have evolved to be highly sensitive to sound, for survival, for communication, for connection. But what happens to our internal soundscape when we imagine being in true silence? Astronauts often speak of the profound quiet of space. While their spacecraft are noisy due to fans and life support systems, the moment they are outside, performing a spacewalk, is often described as an experience of deep, almost overwhelming silence. It's so different from anything on Earth that it can be disorienting. Yet many also describe it as profoundly peaceful. It allows for a different kind of focus, a heightened awareness of their own breath, their own heartbeat, the gentle movements of their body. In that ultimate quiet, the internal world becomes amplified. This mirrors what happens when we seek quiet here on Earth. When you find a truly peaceful environment, perhaps late at night in your bed, as you are now, your external sensory input diminishes. And what happens? Your internal world, your thoughts, your feelings, your bodily sensations become more prominent. The gentle rhythm of your breathing, the soft beat of your heart, the quiet hum of your own consciousness. The universe, in its grand, silent performance, invites us to listen differently. Not with our ears, but with a deeper sense. To listen to the light that travels across billions of years. To listen to the subtle pull of gravity that holds galaxies together. To listen to the whispers of our own minds, uncluttered by external noise. This cosmic silence also reminds us of the fragility and preciousness of our own sound-filled world. Our atmosphere, a thin blue veil, is what allows us to hear the wind, the rain, the voices of loved ones, the melodies of music. It's a gift, this envelope of air that lets sound exist. Without it, the vibrant auditory tapestry of our lives would vanish, leaving only the silent hum of our own internal experience. The very sounds we often take for granted, the crackle of a fire, the distant rumble of thunder, a child's laughter, miracles born from the existence of a medium to carry them. The resonance of absence, it's fascinating to consider how we experience absence. We often define things by their presence, but absence can be just as potent. The absence of light is darkness, the absence of heat is cold, the absence of sound is silence. But these absences are not merely nothing. They are conditions that allow other phenomena to be perceived more clearly. In the profound darkness of space, the stars truly blaze. In the intense cold, matter behaves in strange and beautiful ways. And in the utter silence, the universe reveals itself in a different, notatory language. Imagine trying to describe a silent film to someone who has only ever watched movies with sound. They might struggle to grasp the power of the visual storytelling. Without the support of dialogue or music, the silence to them might feel incomplete. Yet for those who appreciate silent film, the very absence of sound forces a different kind of engagement, a heightened focus on expression, movement, and visual nuance. The silence becomes a character in itself, amplifying emotion and meaning. Similarly, the silence of the cosmos is not a deficit. It's a fundamental characteristic that shapes how the universe expresses itself. The magnificent nebulae, vast clouds of gas and dust where stars are born, glow with vibrant colors. But these cosmic nurseries are completely silent. The violent death of a star, a supernova, unleashes more energy in a few seconds than our sun will in its entire lifetime. Yet it expands into the vacuum without a whimper. These celestial events, which might seem less dramatic without an accompanying roar, gain a different kind of solemn grandeur in their quietude. Their power is conveyed not through noise, but through the sheer scale of their light and gravitational influence. We, as beings shaped by sound, have had to develop tools to translate this cosmic silence into something perceivable. Radio telescopes, for example, capture the faint whispers of electromagnetic radiation emitted by distant galaxies, pulsars, and quasars. These signals are not sounds in the traditional sense, but patterns of energy that scientists can convert into audible frequencies for analysis. So, while space itself is silent, we create ways to hear its electromagnetic voice, turning vast, quiet data into perceptible tones and clicks. This act of translation highlights our human need to make sense of the world through our familiar senses, even when the world itself operates beyond them, drifting into cosmic stillness. As you continue to relax, letting your thoughts drift like nebulae in the void, consider the incredible journey of cosmic dust. Tiny particles, remnants of ancient stars, drift for eons through the silent blackness of space. They don't make a sound as they travel. They don't hum. They simply exist, carried by the gentle currents of solar winds, occasionally colliding with other particles, forming larger aggregates, silently contributing to the building blocks of future stars and planets. This slow, noiseless ballet of cosmic material underscores the pervasive quiet that defines the universe's evolution. Even the gravitational waves, ripples in space-time predicted by Einstein and recently detected, are fundamentally silent. When two black holes collide, a cataclysmic event of unimaginable power, they send out these space-time ripples that travel across the universe. Our detectors, like LIGO, are designed to measure incredibly tiny distortions in space itself, translating these subtle stretches and squeezes into signals we can then interpret. We hear these events not because they produce sound, but because our technology allows us to perceive the fundamental vibrations of the fabric of reality. Vibrations that occur in a realm beyond sound. It's a powerful reminder that the universe speaks in many languages, and not all of them are audible. So as your body becomes heavier, you're breathing deeper, let the thought of that cosmic stillness wash over you. Let it soothe any lingering anxieties. Let it remind you that not everything needs to be loud or demand attention. It's some of the most beautiful things simply are. The universe's profound silence isn't an emptiness to be feared. It's a vast, tranquil presence. A state of being where existence simply is, without fanfare, without clamor. Your own breathing, your own heartbeat, they are tiny, perfect rhythms in your own personal quietude. And as they gently slow, joining the vast, unheard symphony of the cosmos, know that you are not just listening to silence. You are becoming a part of it. A quiet observer, gently drifting in the vast, silent sea of the whispering cosmos. Busy, noisy world, the thought of this ancient, silent light embracing us from every direction can be deeply calming. It's a cosmic lullaby, a constant, subtle assurance that even in the vastness and mystery, there is an underlying rhythm, a foundational whisper that connects us all to the ultimate beginning. So tonight, as you settle in and let your thoughts drift with the stars, remember that even in the quiet, even in the dark, the universe is always humming its oldest song. You are enveloped in the light of creation, a gentle warmth from the very dawn of time. Perhaps as those ancient photons pass through you, you can feel a sense of connection, a subtle echo of the gentle hum that permeates everything. And now, as we bring this quiet journey to a close, let me ask you again, where in the world are you listening from tonight, and what time is it right now? Wherever you are, and whatever it is, thank you for spending this time with me. If this video helped you wind down or sparked a quiet wonder, I'd be truly grateful if you gave it a like and tapped subscribe. It helps others find their way here to this calm little corner of curiosity. And if this video kept you awake, well, at least you might have learned something truly profound while waiting for sleep to find you. Until next time, rest well, and may your dreams be filled with the gentle hum of the universe.